So I'm going to talk about one very specific environmental stressor, if you like, and that's air pollution. And if you'll sort of allow me, I'll spend most of the first half giving you some context to this as an issue, and then perhaps in the second half talk a little bit about some of the research that's occurring at York at the moment. Now, air pollution as a science research area is something of a Cinderella, or has been something of a Cinderella. It's been around for a long time. It sort of lacks trendiness in certain environments. So I'm going to try to persuade you to start with that this is really still a science area worth studying. And perhaps the really most basic starting point is to see how it impacts on us in terms of our health. And there's a really interesting history to this. And if you go back in time, the very first person to identify air pollution as an issue was Hippocrates. And he basically invented occupational health. And he was particularly concerned about stonecutters and their exposure to dust. And if you like, he was the first person to really raise this as an issue, because of what you breathe in may in fact impact on your general well-being. And then it's Pliny the Elder, a little bit later, who was the one who essentially began to realise that there was a rather complicated mixture of entities in air. He was particularly concerned about how it might impact on his health. He didn't like smells, he didn't like sewers, but he was most concerned that he thought that air pollution would impact on the quality of his wine and his beer. So almost all of Pliny's writing on air pollution is about the degradation of wine quality. So this is the really sort of long-term historical context. Air pollution, as we perhaps understand it, again, has followed very much climate trends in that it accelerates away in the 20th century. And a very fascinating way to examine the overall impact of this on the globe. It's rather easy to think about air pollution as a sort of local issue, you know what's in the street outside you, but you have to scale up and look at the globe, is to look at the impacts on deaths. So it's rather small writing on some of this, but this is the assessment of causes of death of everybody in the 20th century. And you can see some of the really big topic areas here, so non-communicable diseases, cardiovascular diseases, something called humanity, that I'll zoom in on in a moment, infectious diseases and cancer. So this is a very cheery slide, and basically within this are all the possible things that you may die of, or you people have died of in the 20th century. And if you zoom in on the central section to this, you can now begin to make out some of the boxes, sorry, some of the circles here. And the one that I want to draw your attention to here is the box here, which is the estimate for the number of deaths in the 20th century due to air pollution. It's 110 million deaths. So it puts it slightly above tobacco, which is this one here, and about the same as the First and the Second World War combined. I'm not sure of your political persuasions, it's also more than communism, which apparently is responsible for 94 million deaths. So this is this is based on a Wellcome study and WHO data and so on. So there's lots of generalisations and things, but you get the sort of scale of the problem here, and it's certainly just on the corner of this particular slide there's a few cancers. And air pollution, for example, has been a larger killer of people in the 20th century than stomach cancer, liver cancer, and some of these other very major killers. So that's the historical context to this. So there are very large impacts on people. What I'm not really going to have any time to talk about is there are also very large impacts on ecosystems, and particularly at the moment on crop production, which is almost a sort of a side component to this of very high economic relevance at the moment. Okay, so if you look at Europe and you come fast forward now to 21st century and you look at the estimates of how air pollution impacts on people today, this is the estimate for the average life expectancy reduction in Europe, which is shown by this particular graph here. Now you can see there's some odd things here. It's not good to live in Belgium. Okay, you can see here Belgium has a very poor reduction in life expectancy. Nothing really that the Belgians are doing. They're just very poorly located in terms of meteorology and industry and so on. And you can see that some of the numbers here are relatively modest. Some of the whites and the blues here essentially suggest that your life expectancy is reduced by only a month or two. But you can see there are large chunks of Europe, including parts of the UK, where life expectancy is reduced by, on average, perhaps a year. And the average hides quite a sort of multitude of sins, and really we're not interested so much in the average as whether it's going to impact on us. And in fact, if you are a vulnerable grouping, this is from the House of Commons Environmental Audit Committee, if you're a vulnerable grouping, meaning you have respiratory illnesses, pulmonary diseases, sort of asthma and so on, you are disproportionately affected by this particular pollutant. So there your life expectancy is reduced by potentially anything up to 8 or 9 years. And that really is a very significant reduction in your life expectancy. So sometimes with these, when these statistics are used, you have to be aware about the averaging effect, making it look rather insignificant. Whereas if you're in one of those groupings, and who knows in this room who will go on to develop pulmonary diseases, for example, this may substantially shorten your life expectancy. Now, this is not a problem confined to Europe. This is a global problem. And what you find, of course, is that it's not just what you do, what industry you have, what state of your vehicle fleet, and so on. Also, a lot of it depends on your geography. So you end up with rather unusual distributions of impacts. And so this is a rather difficult to read graph. What you have here is a graph that shows basically the fraction of your population by a whole set of countries, I think about 40 countries on here, exposed to a particular threshold in particulate matter. That's 2.5 micron sized particles. And so the people who are doing really well, you can just make out at the top, so very, very small fractions of the New Zealand and the Icelandic population and the Finnish population are affected by particulate pollution, not because their cars are necessarily any better or cleaner than cars in some of these other countries, but because their geography places them in remote locations where meteorology is essentially their friend. They have a lot of fresh air brought in from outside. And you work your way down the list, and then you begin to get some very high thresholds for countries down here. And you can see some of these at the bottom: Czech Republic, Belgium, Germany, Hungary, places in Central Europe, where very large fractions of the population are exposed to high pollution levels, particulate levels in this particular case, again, by dint of their geography as well as what they do. This is what I'm going to talk a little bit more about, is how this transport of pollution, effectively being impacted by what other people do upwind of you, can lead to some of these very, very large disparities in exposure to particular pollutants. If you're struggling to see it, Britain lies in here, about the same as Turkey and France and Japan, and there's a really big, very, very high exposure here to very high levels associated with China, which is probably suffering from the worst of any of the countries that are here. Okay, so this is the sort of impact side of air pollutants. It isn't an unremittingly negative story, though, and we want to be slightly upbeat about what can be done. And air pollution is perhaps a very good example of where there has been sufficient inertia to introduce policies that have genuinely made a difference. And this is a very sort of, the next few slides are rather sort of London-centric, but this is data for the UK from about 1994 onwards for the pollutant nitrogen oxides. This is the sum of nitrogen dioxide and nitrogen oxide. And this is essentially released from vehicle exhaust, and it's something that's been very effectively tackled from gasoline engines through the introduction of catalytic converters. And actually, when you think about it, this is a very, very expensive tax, effectively, the introduction of catalytic converters, but it's one we've all bought without too much complaint. Obviously, a lot of policy interventions are ones that come with substantial loud voices saying that they're going to cost us. Well, because a catalytic converter adds about £1,500 to the cost of a medium-sized car. So this is a substantial tax that you're receiving to receive this benefit. But what you can see is, since the introduction of what we describe as Euro 1 standards and catalytic converters, nitrogen oxides in central London really began to fall pretty rapidly. So most air pollutants are pretty short-lived. NOx only lives for a few days in the atmosphere. So the impact of your intervention is very, very fast in this particular case, and you can see over the first 10 years, the levels of nitrogen oxides fell pretty rapidly. The exposure in London fell pretty rapidly. But you can see the sting here, which is from about 2004-05 onwards. We are no longer seeing improvements in the exposure to nitrogen oxides. This is actually recreated in quite a few other pollutants as well. And this is now where the main challenge in air pollution comes, which is that there were some very early gains in developed countries through introducing particular control technologies, some of them pretty expensive, which made some very, very immediate improvements and impacts on air pollution, particularly in urban environments. But some of these benefits are not continuing, and of course the cost of implementing this is exceptionally high. Billions of pounds will be spent in the next 5 years on further improvements to vehicle exhaust controls, for example. So if you look at it over a decade, you can see that large parts of Europe have seen substantial improvements, for example, in NOx, a trend downwards of a few percent a year. But this is beginning to level off now. And of course, a lot of this is, well, we have to understand what the sources of this are. When they were up here, the concentrations were very high. We were pretty sure that most of the sources were local. It may be that now what we're seeing is some places that are not regulating their pollution as well. So this is a hypothesis that we can examine. And it's worked very well, the control of various other air pollutants. If you take toxic persistent organic pollutants like polycyclic aromatic compounds, dioxins, furans, these sorts of things, really very effective examples of policy controlling these in air. These are carried by particulate matters, very, very strong interventions introduced in the 90s, and actually if you now look at the ambient, or the concentrations in ambient air normalised to the values of 1990, really, really significant reductions. Yeah, so it's an indication that things can be done. And again, for certain pollutants here, you can see sulfur dioxide has been very, very effectively tackled. This is London data, but it's been tackled very well in most of Europe. Carbon monoxide has gone down substantially. But another tricky one here, PM10, particulate matter more than 10 microns in diameter, that one doesn't appear to have gone down, despite the introduction of lots of technologies. There are some mysteries here, and some things that people would very much like to get to the bottom of in understanding why these trends are doing what they're doing. Because they cost a lot of money. And regrettably, the things that are not going down, the things that are really doing you harm, like particulate matter and NO2, are the ones that have stayed flat. Some of the ones like CO2 and CO, which did you rather less harm, are the ones that have gone down. Sod's law. And the final one, which is sort of considered as a classical air pollutant, is ozone. And again, ozone pollutants, ozone chemistry is rather complicated. This means that this is something that has actually crept upwards over the last 10 years for reasons that I'll go into a little bit later. So there are some trends, and there are some secondary species, particulate matter and ozone, which are particularly susceptible to transboundary transport. These are things that don't seem to be declining as we would like to see them go down. Right, so how do we scale up? So when you actually think about where emissions come from, you start at the street scale, and this is of course a model. We don't have any data on this sort of resolution, and you can see that in an urban environment, the vast amount of air pollutants are coming out of road transport, and you can see here this is a model of the estimate of where emissions are coming out. You see they're always higher at road junctions than they are in the middle of the street, because you're idling and you're accelerating. And you can see here, you can get a very nice map of the distribution of pollutants, and it is only that. It's only an air-modelled map of where they're coming from. And you can keep scaling these up to produce something like that, which is the map of the emissions of nitrogen oxide, MnO2, from London. And you can take that in turn, and you can scale that up to a model that's, say, the size of the UK. And as you go from this thing to this thing to this thing here, you have to factor in three things. The emissions, that's essentially what drives the first picture up there, what's coming out the back of the car. Then you have to factor in some chemistry, because none of these pollutants are static, they all react. So you have to include their chemistry and their reactions. And you can see when you get up to the scale of perhaps London and greater, now you have to start to factor in the meteorology as well, because the movement of all these is then defined by the winds. There are interesting features. In fact, if you plot London, the prediction for 2020, and you look at it from space, the centre of London appears to have moved out here, and that of course is Heathrow Airport, which will be emitting more NOx than the whole of central London in about 5 years' time, according to emissions estimates. So London from space will have moved about 30 miles centrally. So that's the picture. But again, all of this is model, and this is one of the tricky things here, because the amount of measurement that we have to constrain all of this is rather small. So a lot of this is based entirely on model prediction. So if you look at London in particular, I like this as a paper, because this is an old paper, and it proves that you've read some papers that go back more than 10 years. And this is essentially the first paper that really talks about modern air pollution in London. And it highlights the deficiencies of the knowledge of chemistry at the time, or the importance of understanding the chemistry. And it's sort of a typical paper, which is someone moaning about building a power station. It's a Battersea power station in this particular case. And for the air pollutant nitrogen oxides, which are reasonably easy to understand, they come out the back of your combustion process and they blow with the wind. And they came to the not unreasonable conclusions that if you were downwind from the power station, you saw more nitrogen oxides than if you were upwind. And that all seemed very sensible. And so there were some air pollutants that even back in the 20s and 30s could be assigned pretty neatly to sources and predicted depending on the weather and whether the power station was running or not. The difficult ones were the secondary pollutants, of which ozone was the one that was identified. And the description of ozone here is that, just seeing the lot of it, it says it was varied by variations in the amount of ozone in the air due to factors that we can only guess at and do not understand. Now this is, of course, highlighting the fact that the chemistry of secondary pollutants is rather fiendishly complicated. There is no nice, simple relationship between undertaking a certain process and a certain amount of pollutant coming out the back. There is complicated chemistry here. And depending on what sort of atmospheric chemistry you do, you draw the cycles of air pollution chemistry in different ways. So if you're a big person who measures ozone, you rearrange this sort of graph here to put ozone in the middle. If you're a NOx person, you rearrange the graph to put NOx in the middle. This is probably the most reasonable format of showing the chemistry of the troposphere and how pollutants react. And it's to put the hydroxyl radical in the centre, the OH radical. And if you follow the reactions here, what you discover is almost all of the big emissions from anthropogenic activities are all, in one way or another, eaten up by the hydroxyl radical. So if you take carbon monoxide, it reacts with OH. If you take organic compounds, they react with OH. So does methane, so does NO2, so does SO2. So all of these pollutants essentially spiral out into secondary products from this set of chemistry. And what's significant here is that all of the reactions in this complicated scheme, and there are tens and tens of thousands of these, all have different timescales. And some of them react extremely quickly, a few seconds, which essentially means that because the transport element, the metrology element, is insignificant. And some of them spread to many, many months. Of course, that means in many months you can move your pollutant a very substantial distance. And it's trying to understand which ones move and which ones don't move, and how some of these products might move from one place to another. But it's probably going to be the key to understanding what our trends in air pollution are going to be over the next 100 years as we begin to move more things on global scales. Now, the best example of showing a long-lived pollutant is to pick carbon monoxide. So carbon monoxide isn't really significant in the UK anymore as a pollutant. It very rarely exceeds air quality thresholds, but it has a very long lifetime. And so it's also one of the few air pollutants that you can see from space. And so if you look for carbon monoxide from space, and this is from the MOPIT satellite, you find this quite nice picture. And it basically shows that you have lots and lots of hot reds over here, which is carbon monoxide from east coast of the US blowing out over the Atlantic and arriving in Europe. And you can then see pollutant in Europe blowing out over Russia, and you can see activity over here in China and so on. And so satellites have given quite a lot of insight into how the very long-lived pollutants actually blow around. And all they're doing here is following weather systems. So this is just following the storm track over the North Atlantic. But once you go to this global scale, suddenly the picture becomes rather complicated, because I didn't think they had a huge number of cars in this part of the world here. Or I didn't think sort of northern Canada was particularly a hotspot for road transport. And of course what you then discover is the things that in an urban setting you describe as a pollutant turn out to be released also from other activities that go on and from natural processes as well. So it rather complicates the description of what is a pollutant. When is carbon monoxide an air pollutant versus when is it part of natural biogeochemical cycles? It also then makes it very difficult to attribute sources to one or the other, because you're not really sure for a particular chemical whether it's come from a man-made source or a natural source. This makes understanding some of the trends that we see more complicated. But so I put it in inverted commas that not all pollutants come from anthropogenic sources. And what we rely on is surface measurements, essentially, in very remote places to try to untangle this. And on the face of this, this looks quite hopeful, because the WMO coordinate networks of activities around something called the Global Atmosphere Watch Programme, big surface network of stations. Now, you would think if you have enough surface stations located around the world, you can see all these pollutants, you can track them, you can work out which ones are from natural sources. What you discover is that these are officially all the measuring locations that exist within the WMO network, and the world looks pretty well covered here. But when you dig beneath the surface, what you discover is that many of the pollutants that you'd like to measure simply aren't being measured at the locations that you'd like. So if you take something like surface ozone, now if you're an atmospheric chemist, ozone is very easy to measure, very, very straightforward. The number of measurement locations has dropped dramatically in some of these background environments to this number here, which is sort of okay, but you wouldn't say that was a particularly dense network for the globe. And if you then want to measure something a bit more esoteric again, you want to measure an organic compound, an air pollutant, your network has diminished to this, which is by no stretch of the imagination a global network. And so what we've run into is a problem that in the background environment, where there are also co-releases of pollutants that contribute to this global burden, our observation database is essentially empty because we don't have any measurements there. So we're sort of left with lots of information on what's going on in the urban environment, but with very little about how these chemicals are behaving when you get to the background environment. So I have to put this up because this is a York activity, and it's something that we're very proud of, that the sort of places where these things are measured are at observatories. And this is one that York runs out in Cape Verde. And you can see why these locations are picked. This is where the observatory is. A, it's a nice place, but also it's representative of this big footprint of atmosphere here. Essentially, all the air that you get there has travelled over part of the North Atlantic. So all of these measurement stations are located in order that they're representative of big footprint of atmosphere. And even in some of these very remote places, there are impacts of pollution at very, very low levels. This is a graph here which shows essentially how the small changes to the level of nitrogen oxide can change and perturb the amount of ozone. Now, this amount of nitrogen oxide, 10 parts per trillion, is vanishingly small. 10 or 12 parts per trillion is incredibly low. But what you see with this is that as the amount of nitrogen oxide, which has just reached there from very, very long range transport, increases, it begins to perturb natural ozone cycles here. So although sometimes the concentrations here look minuscule, they can have impacts on chemical systems that are in very, very, very fine balance. And ozone loss is a process that's an extremely fine balance that can be perturbed with minute quantities of increases in particular pollutants. Or in this particular case, increases, for example, in shipping may tip some balances here. So above the surface, and this is an activity that we are now very heavily involved with at York, which is to basically detect pollution transport above the surface. And you can't see everything from space, and you can't see everything from satellites, unfortunately. So the only way to really tackle this and to see air pollution moving over sort of continental and hemispheric scales is to use research aircraft. And there are basically two ways of doing this. One is you get together lots of research aircraft with really big budgets and you fly them all together in spiders' web patterns to essentially track the movement of air pollution over large scales. Or the other is to essentially use piggyback on top of commercial aircraft and put measuring systems inside those. This is a particular example run from Europe, which flies from Frankfurt on all these different routes here. So that's the only way to make really, really detailed chemical measurements in the free troposphere, the upper troposphere, and lower stratosphere in really high detail at the moment. So to give you an example of a sort of natural stroke unnatural pollutant, this is some measurements just showing the impacts, for example, on forest fires. Now, forest fires, you'll hold your own opinions on whether a forest fire is a natural or an unnatural process. It has a sort of number of forces working in its favour or against it. This is from northern Canada, but it is a big source of chemicals to the atmosphere, and they're rather poorly quantified. So to actually understand this, you have to get in amongst this and watch this plume transport downwind. This is something that's done from the UK research aircraft. This is a sort of big 4-engine jet. Measuring in northern Canada here, so over space scales of perhaps 500 to 1,000 kilometres. So watching these combustion processes loft out over the Atlantic to see how this is contributing to the overall chemical burden that we have in the Atlantic and how that affects the background that we have in the UK. To do this, you need lots of equipment. This is the sort of thing that I do for my research. So you take the aircraft and you take the seats out and you reinstall things like mass spectrometers inside, or here there are lots of canisters used to collect air samples. You bring them out, you do really detailed analysis on this. It's the sort of thing you can only do on a research aircraft. What you discover through these forest fire plumes blowing out over the Atlantic is you discover a whole range of chemicals, some of which are what would notionally be described as air pollutants. So there are things in here like toluene, it's not shown, but there's species like benzene, toluene and xylenes which are regulated as air pollutants, which are also released as byproducts of combustion from forest fires. So this is why it's going to be difficult to understand the trends in these, because we'll have superimposed over our trend in the anthropogenic emissions, trends in semi-natural emissions such as this. So we've looked at particularly at a species like benzene, and we've looked to see where that's been coming from, and by scaling up the observations, so by taking a model, and by taking some Earth observation data, and by taking some data from an aircraft, what we then begin to calculate is how much benzene, which has a regulated air pollution limit, is actually coming from forest fires themselves. What we discover is not significant for us in the UK, but there are large chunks of the world where very significant fractions of their benzene actually appears to come from forest fires rather than vehicle exhaust. And because the way to really validate this would be with your surface sites. What we've tried to do here is to validate our model predictions with what we've seen at our Cape Verde Observatory. But we only have one measurement location in the world to actually compare to, because it's only measured in one place in the remote environment. So we're really, really data poor. Which brings to my last couple of slides, which is that we would really like to enhance the background capability to measure air pollution in remote places. This is also Borneo. This is also one of the last bits that hasn't been turned into palm oil plantations, seen from a research aircraft. We would like to get chemical sensors in these remote places. You know, we're well equipped in central London, but we have nothing in great chunks of the world. We'd like to do this. The reality of when you do it is it looks like this. You drag some 10-ton shipping container through the mud, and you struggle to keep the thing running for about 6 weeks, and then you pack it in and go home, because it is so difficult to do. And the reason it's so difficult to do is that we have technology limitations on this. At the moment, this is what I would describe as quite a compact instrument for measuring my benzene in air. It is not a compact instrument by any measure, stretch of the imagination. The things we are using are too complicated, they're too complex, they require too many operational requirements, like air conditioning need people. They're not feasible. This is one of the reasons why we are so data poor on air pollution in the background environment. We also can't even calibrate some of these instruments, and there is no global traceability in data, and there's very little data interoperability. So there is an awful lot of work to be done. So one of the things that we were very, very keen to see happen over the next 10 years is the promotion of smaller, more compact devices for the future. This goes across all air pollutants. All at the moment, there are all great big boxes that require lugging about in shipping containers. We would like to see these things miniaturised, because only when they're miniaturised and they have lower requirements for power, for consumables, human intervention, will we actually place them into remote locations. This is a particular example of devices that we've tried to build made out of glass microfabrication that can measure organic compounds, but there are lots of other ways that this could be done in the future as well. Again, trying to microfabricate things with gases and liquids. Something that's been done very, very successfully in the bioscience and medical research community. We think it's got to be done in environmental groups as well, in order to try to reduce the size and complexity of devices. So my key points just to sum up with, which is that urban emissions in Europe are actually in steep decline at the moment, but we have very strong growth elsewhere, in Asia and in Africa. But our trends in pollutants are not necessarily following our emissions. So our trends are now flat for many of the key species, NO2 and particulate matter in particular, slightly upwards for ozone, and this is almost certainly in many cases due to transboundary transport of pollution in from other locations. And that there are also some rather complicated and rather poorly understood interactions with natural emissions, where the same species that's regulated in an urban setting is also released from a natural process. Disentangling those is extremely difficult to do when you have no data on the natural emissions. And again, overall, we're limited by detection systems which are lacking for remote locations, and we need to adopt new technologies. So I've stolen lots of stuff from other members of staff in chemistry, too many to acknowledge, but some of these key people up there, and so we're all very lucky to receive funding from all of these different organisations.